Thank you very much, and also Shamridi, who is he? He's not there. Thank you very much for inviting me and for organizing everything. Actually, this is our first time, Eric and mine, to India, and it's a very nice experience. It's a very beautiful country. People are very welcoming, and we are very glad to be here. It's also very hot and spicy. So my talk today will be about statistical physics of athermal sheared disordered systems. And so this change title already indicates that I believe in the phase transition scenario. And I will start by showing you the place where I'm from. So Grenoble is in France, which is in Europe, as most of you will know. Some of you might have been to Paris already. Few of you probably to Grenoble. Yes. Few of you to Grenoble, which is situated here, very close to the Swiss and Italian border. And in Europe, Grenoble is known for physics because there's the European synchrotron, the ESRF. For example, Damien already did some experiments there. And there's also the ELL, which is the French, German, British neutron scattering facility. The university, however, is not on this side of the campus, but on the other side of the city. And you see all of these places are surrounded by mountains. So everything of this is within the French Alps. It's a very nice place. And I'm working in the group Statistical Physics and Modeling, which was founded by Jean-Louis Barras, with many of you who many of you know, probably. And he founded this group only in 2013, so it's very new, and has already many members. And the work that I'm presenting are mainly done by Jean-Louis Barras, and then also initiated by Lideric Bouquet, and also in collaboration with our PhD student Chen Liu, and Alexandre Nicolas, who just finished his PhD on mesoscopic modeling. Then there's Elisabeth Agoritzes, who does the mean field analytical calculations, and Eric as well. And then I work together with Francesco Pozzi, a former postdoc of the group, who's now at the INS Lyon, who's doing the molecular dynamic simulations, and Ezequiel Ferrero, who is also working on the mesoscopic modeling. And then I have to mention also an important collaborator in Marseille. He's from Applied Math, Julien Olivier, and he's also working on the analytic descriptions. So now let's come to the physics. So here I have a picture of different systems, gel, foam, and granular matter. And of course, these look in appearance very different. But if you think of a more coarse-grained level, maybe since they share some common features, we can also find some common description for these type of systems. So what is similar in all those systems is that at the scale of the individual particles, bubbles, or atoms, they are disordered. And when you shear them, they show a very heterogeneous response to the shear. So you see fast particle rearrangement that coexists together with the elastic response of the system. If you shear with a very small force, typically these things behave solid. And if you shear strong enough, then it will become a fluid. So there's a solid to fluid transition in these systems. This idea of this local rearrangement or shear transformation zones, plastic events, there are different names in the literature, has been first introduced by Ali Argon in '79. And to fix a little bit the vocabulary, I will always, when I talk about the microscale, I talk about the scale of individual particles. If I talk about the macroscale, I will talk about average quantities over the whole system. And then we introduce a new scale, which would be the mesoscale, which is the typical size of a plastic event or rearrangement. So,
what is the typical size of plastic?
That's a good question. So, it doesn't exist. You can. You have a power law decay, but you can, for example, say from that point where the Eshelby description becomes has a meaning. Or you do, for example, Voronoi.
So the core which you have defined, right?
Yes. So The macroscopic response to steady shear is shown here in two different systems. This is a foam. This is a stress-strain curve, or force-strain time curve in this case, which is equivalent. So you see there's this first transient regime, and after a while you go into a steady-state regime with large fluctuations. So this is even simpler than the hard amorphous systems because you don't have the shear hardening, you don't have the breaking. This is foam. This is sheared foam. It's an experiment by Isabelle Cantat and I think it's Olivier Pitois in Rennes in France. And yes?
Statistics also study about statistics.
The statistics is what?
Drop of this
yes.
Course. Is this statistics known or studied?
In this experiments they don't, I think. But in principle, people study these things, of course, yeah, within the steady state. So and then here, then within here, this is a typical flow curve where what you do is you take the average value of the stress in the steady state and you plot this versus the shear rate, which gives you these different curves. And this is a gel. So I will talk a lot about the form of these curves in the finite shear rate case. And the microscopic response looks the following. So here are different systems. For example, a 2D Lennard-Jones system. So this is molecular dynamics, or this is quasi-static simulations of a 2D Lennard-Jones system, where you see in the instantaneous velocity field some very heterogeneous events happening within the elastic matrix. And then this is an example of an experiment it's very recent, by Jensen, Weitz, and Spepen. And this is the shear of a colloidal glass, and they look at the spatial correlation of local strain. And again, they see this fourfold structure in the plastic response. And then also here, there's a granular material. And even there, you can see in the spatial correlation of the local strain something that looks quite quadrupolar. Maybe with a different angle, but still there's the signature. And then here, this is a very nice experiment. I think this is the only one that I know of where you really measure the stress redistribution in the system. And this is done for 2D emulsions at the high packing fractions. And there as well, you see this very nice quadrupolar symmetry in the response. OK, so the main question is, how can we combine what is happening on the microscale, this very non-isotropic response on the local scale, to what is described on the macroscopic scale by stress strain or by flow curves. And the idea is to bridge these two things using statistical methods, tools of statistical physics. And first question that you have to ask is, what are these individual events? So there has been a study by Eshelby in '57 who asked the question, when I have locally a rearrangement, like we saw before, a change of form within the elastic matrix, which is homogeneous, what would be the solution for spherical inclusion in a simple shear 2D in terms of Green's function? And the Green's function would look like this if there's no dilation, for example. This is the simplest form that you can get. So it's typically Longrange, the kernel. It's 1 over r to the power 2 in 2D, 1 over r to the power 3 in 3D. And it has a very isotropic form in this part, an isotropic form in this part. So this is what it looks like here. This is the stress change due to a single plastic event. And this has been verified very recently in a paper partly done in our group with Jörg Röttler. And what they do, they initiated, so they induced local shear transformation in the Lennard-Jones system by dispersed Lennard-Jones system. And they look at the response which is triggered by this local induced transformations. And if you average the response, first of all, you have the displacement field at long times, and you average this over about 40 to 50 realizations. You see this beautiful picture, which seems very much like the theory. And if you compare more quantitatively, I'm very sorry, more quantitatively, you see that indeed here the simulations fit very well the Eshelby predictions. So this is the finite size effect. This is due to the borders of the system. However, there are some important things from the study. So Eshelby fits extremely well, average quantities in the long time limit. But depending on the damping coefficient, for example, this Eshelby response, which is not instantaneous, will depend whether you have strong or weak damping, and it will be diffusive for the strong one and ballistic for the weak one. More importantly, maybe even, is that fluctuations are actually quite strong. So here, what this shows here are the fluctuations in the displacement fields corresponding to the different realizations. And you see that, well, at the low distance regime, you can still say, well, maybe they are negligible, but at some critical distance, they even becomes larger than the actual response. This might be important for the dynamics. Okay. In the following, however, I will derive results from a very, very simplistic model that doesn't take into account all these dynamical issues. And so the MESA model that I present to you here is a model that has been introduced in another form already before by Buladov and Argon. Also Damien worked on this with Stefan Roux. And the one that I present to you really is the one of Picard et al. So the idea of this model is you have the main ingredients, which is the elastic deformation. Beyond some critical stress value, you will induce plastic events that redistribute the stress, and that can lead, once created, to a stress increase somewhere else that will induce another event to happen. And with this, you need also some rules for the yielding. So you need to say, when do I produce a local yielding? And since these systems are healing systems, it's not like a fracture, but it's really, you have an event somewhere, and afterwards, after some time, it relaxes to the elastic state again. So you need also some rule to describe this relaxation to the elastic state. So the minimal ingredients that we take, I already said this. So plastic events, elastic stress redistribution, described by this very simple propagator proposed by Eshelby. Then we consider athermal systems. I want to highlight this again. And this means we can neglect thermal fluctuations. And we consider, for simplicity, periodic boundary condition and simple shear, which allows us to describe the problem with scalar quantities. Okay. So the model of Guillemette looks as follows. So you have first the elastic response. So the stress is just the stress change in time is just proportional to the shear rate that you apply. This increases the stress in the system up to a point which you reach a certain yield stress, and you will produce these Eshelby kernels that are convoluted with the plastic strain field. Yes.
Mu is taken to be same for all.
Mu is the same for all. It's a simplification.
So this is already ignoring the heterogeneity.
Yes, it's ignoring the heterogeneity in that part. And the plastic strain change is described here as a local exponential relaxation in the field. So this N here actually, so I have two fields. I have the stress field and I have the activity field, as we call it. The activity field tells you whether locally I will produce an event or not. So N is either 0 or 1. And the rules to become plastic is when I exceed a local yield stress, the state variable goes to from 0 to 1 with some rate. So there's some stochasticity. And also in the relaxation dynamics, towards the elastic state, there is a rate here, a rate function that introduces some stochasticity. So the randomness in this dynamics comes from these rules.
So this is written for the I represent the one unit, right, of the lattice.
Yes. Sorry. This is I.
This is written for each individual variables on this lattice.
Yes.
Now you assume that when there is an event happening, the modulus goes through 0.
The
shear modulus goes to local shear modulus will
yes,
go to 0.
yes.
And this equation will become what?
No, so you're talking about mu.
Yeah.
It's not going to 0 here. So it's a cost-grained description. In reality, it goes to 0, but it's a cost-grained description where you will just describe the stress, and you don't describe the last part. You just say it's going up and down again. So you don't have this time scale over which you flatten, let's say.
And why only stress change is distributive? Why some of it can go stored?
Why it can be restored?
Why can it be stored? Why you don't have storage? You know,
It's storage here.
All the epsilon, no. If you don't have gamma naught,
Yes.
from the change in sigma, you assume it's all in epsilon plastic. Why it's all in epsilon plastic, you don't sum in epsilon, no, in gamma? You know, why a change in sigma cannot be translated partly to dissipation?
So this is described, so this is for a fixed shear rate. This is a model for a fixed shear rate.
For fixed?
Shear rate.
Yeah,
So,
understand, but still.
so then the elastic storage is in this part. If
That's
everything is zero.
That's for the external. But
Yes.
now you have local changes in stress.
Yes, it
false, right?
yeah, so now you have Van Eschel be somewhere.
So
And this changes also the stress everywhere. And this is the storage, elastic storage of the stress elsewhere.
I'm not quite sure why all the epsilon dot is plastic. Why don't have a sum of plastic and non-plastic? And I mean, plastic means distributive, right?
Plastic means,
Fully irreversible.
so, but this is local, right? This is the local. Locally you get plastic, and then
okay.
so then once you you take the dimensions away, and then you see that this model remains with very few parameters, which is basically the shear rate and the system size, which are external parameters that you control. And then the other parameters that appear are these rates that you choose. So it's really, really very simplistic. And the aim of this model is really to test some general features. It's not to be very realistic, but to see what are the ingredients to put into this model to go closer to reality. So now, when we look at the rheology of sheared systems, there can be, in my opinion, two scenarios. One is the continuous transition, where if you increase the shear rate, you go always through a homogeneous flow. And this is described typically by a Herschel-Barclay type description. Then, in some systems, you can also have a discontinuous transition, where instead of having this homogeneous flow, you have a non-flowing region and a flowing region. So this is like a phase separation. And in the flow curve, this can be seen either through a negative part in the stress shear rate dependence, or this is for small systems, or if you go to large systems that really do the phase separations, you will have a plateau. Note that it's very difficult to distinguish this yield stress, for example, also in experiments, this yield stress plateau from this real plateau. So usually you need to look at more mesoscopic or microscopic quantities to really show that this is shear bending, and from the flow curve it's difficult to detect. So we showed that with our model we can also produce this scenario. However, in this talk, due to time limitations, I will only concentrate on this part. So the part on the continuous transition. And I will ask the question, what are the dynamics close to the transition? So here you see some simulations of the model that I just showed for different shear rates. And you see that if you lower the shear rate, the dynamics become much more heterogeneous than in this case. And you can see here popping up the different Eschelbs. And you see also that due to the long-range interactions, you have some noise created even in parts which are not plastic, right?
So it's like behind these two scenarios, you still also start with the linear flow regime, which then subsequently shear bands beyond. So where's that going?
Linear flow, so we are always in the steady state here. I'm talking about, not about transient, but the steady state velocity profiles. So you shear for a very long time, and this is what comes out in the end. So I'm not talking about trend. Of course, there are also, so if you have an age system and you have a stress overshoot, there are all this phenomenology that you get shear bands.
But in those then you are not considering shear bending, the second scenario.
In this talk, I won't talk about the shear banding.
So there is no shear band.
So the second scenario there is shear band. That's what I was
I
saying.
agree. That's what I'm saying. Second scenario is not being discussed ever.
So there's some confusion of what calling a shear band in the community. So for me, these shear bands are bands of flowing regions that persist in the steady state. So it's different from dynamical heterogeneities that you can have, or slip lines that you can produce even in this scenario.
But that's the right definition. So there is no controversy.
Yeah.
Just to mind.
There are people in the community that call slip lines also shear bands, or in the heart, yeah, I think there are, but okay. Going back instead of 4.
So this, like you remove this modulus, it is still somewhat bothering me because the shear modulus goes to 0.
Yes.
And your this stress in individual unit will not try to increase any further.
Yes.
And how do you hit the yield stress for elements?
How do I define it, or?
So yield stress,
So my model is just doing this. I hit at some point the local yield stress. There's some rate to go over it. Then there's the relaxation, and then I become elastic again. So you're saying normally when you do a refined scenario, you have the case that this is really
bend and then become flat.
it becomes flat. This I'm just ignoring. So think of this as a cross-grain view.
So sigma c is, and it will, whole thing will depend on where you put your sigma c.
Yes. Yeah, it's very dependent on that. But then within this model, we are just, so since we just have one value for sigma c and we adimensionalize, we don't see the dependence on sigma c anymore. So it's very simplified, the model.
But you know that this one height actually changes.
Yes, I know. I know. I know, and I will talk about this in a second. Okay, the only thing that I wanted to see here is that there is some noise even in the regions where there are no SLBs happening. So one of the questions will be how describe this noise. So you can look, for example, at stress fluctuations within the simulations and define a quantity that has been studied a lot in the glass community, which is the G4, which is a 4-point correlation function. And here you see a picture of G of R at the most correlated moment. And you see that it's very anisotropic, which might be expected due to the very anisotropic kernel. And also, if you look now at the integrated G4, which gives you the dynamical susceptibility, you see that this one is diverging in time as you go down with the shear rate. So there's the time divergent, and also the correlated volume, which is proportional to the height of this peak, is also diverging.
So this has a long range elastic contribution.
Yes.
If you take a bigger lattice, the chi4 will go up. If you take even bigger, it will go up even further.
Yeah.
If you take even any finite rate, take infinite lattice, chi4 will be infinite.
Which one? Chi4 will be infinite.
Yeah, chi4 peak will be infinity by definition.
No, Chi4, there's a system size dependence on Chi4, no, but it's only limiting it. So if you go to a large system, I don't have the data here, but I can show it. It goes to a finite value.
It's very simple like this. If there is SLB displacement,
Yes.
that's long range.
Yes. At shear rate going to 0, you're right. But at finite shear rates, you have a finite correlation length because you're interrupting the avalanches.
It will diverge only at 0.
You're right in the 0 shear rate limit.
G4 will be cut off.
Yes, it will.
Elastic displacement field.
No, you're in the.
Already long range at any.
You're talking at the quasi-static limit. There it's true. As soon as you shear, imagine you have an avalanche and you shear, you interrupt. You interrupt the avalanche because you will trigger other events elsewhere. Believe me.
This we already did once and failed. That's why.
I can show you the data.
Why don't we get cut off at finite shear?
I can show you the data, and I'm quite sure that I'm right. Okay, here you see a picture of the cumulated plastic activity. And so what we show within the model that there's a real dynamical phase transition as gamma dot goes to 0. This is where the length scale diverges. And so this is apparently similar to the glass transition at TG, but the difference is that length scale can reach really macroscopic sizes, which has been shown, for example, here in this paper. Okay. So recently there has been some works on the comparison between the deepening scenario and the yielding scenario. Just 2 words about the deepening. So elastic manifold in a disordered environment that are driven by external force can be described by the following scenario. So for example, here you have, imagine a rubber band that you drag through the French Alps. Then you will have these pinning forces here. And to overcome the pinning forces, you need to have a critical force. So when you look at the steady state velocity of this line as a function of the force that you apply, there will be a critical force beyond which there's a finite velocity, and there are some exponents with the distance to the critical force, and you can very nicely describe the scenario as a dynamical phase transition from a non-moving to a moving phase. And I insist this is at t equals 0, so this is the ideal curve. Once you have thermal fluctuations, you will have a thermal rounding in this transition. And in the yielding transition, we believe this is very similar. So if you shear the system and at a fixed, let's say you have a fixed stress, and there will be a critical stress beyond which there's a finite velocity, finite strain rate of the system. And the yielding happens at a critical value, sigma c. And at t equals 0, this should be well defined as well. Whereas if there are thermal effects, you can prolong this line up to the 0.0.
Is this analogy or there is a mapping you can do?
So there's no. So Damien worked on this. There are other people working on this. So there's no direct mapping. Already you see that the exponents are different, so it's another universality class. And the most important part is, I'm coming to this now. Okay, you can ask, and the deepening results are already very far, and they studied this in much detail. And it's known from functional renormalization group analysis that the upper critical dimension should be 2 alpha is if the kernel, the interaction kernel in Fourier space goes as q to the alpha. And then, if this is the case, they have predictions for the avalanche sizes, for example, that should scale P of the probability distribution of avalanche sizes should scale with this famous s to the minus 1.5. So there are people saying that this should also be true for the yielding transition, since we have long-range interactions. But the problem is that we not only have long-range interactions, but the interaction kernel is also strongly anisotropic, which makes the problem different. And this proof has been only done for a convex kernel, meaning once you yield somewhere or depend somewhere, all the line will move closer to the threshold everywhere. Whereas here, it's not the case. So there's no analytical prediction for the upper critical dimension in the yielding transition. And simulations suggest, so here are some of our results, but this is also here from work of Lin et al. There are also other works by Boudrique, Saperi, Salerno, and Robbins, and so forth, that show that these exponents, so I don't explain all the exponents, but just to show that the exponents that are typically obtained for the avalanche dynamics close to the critical point are very different from the mean field expected ones, both in 2 and 3 dimensions. So then, is there any hope to describe these systems within mean field descriptions? So it happens that here you see our exponent, for example, at the shear rate goes to 0 limit. But as soon as you increase the shear rate, you see that these curves move to the expected mean field exponent. So this means that maybe as increasing the shear rate, one goes through a regime which recovers the mean field predictions. Sorry. So now.
Is there a start point which suggests, is there some gamma dot which tells you where you go? Where
it goes from one to the other? I don't know what did determines this gamma. So probably one of the ideas would be In the molecular dynamics simulation, I showed you that you have a very nice agreement of the Eshelby and the real dynamics. However, there was these fluctuations that set a cutoff somewhere. So maybe depending on the cutoff of this interaction kernel, there could be a regime that is non-mean field, but then becomes mean field above. So there is a theory for equilibrium transitions which is explaining this. It's, so let me say that in the regime where we see the mean field exponent, there are still avalanches. It's not that it becomes completely random. Is this your question? Right, there's still a... Yes, might be. So the explanation for this is still searched for.
Certainly when you analyze things like earthquake data, there is this issue of what you count as one event.
Yes.
Which determines what
in the global, yes. Yes, yes, we are right now looking at this as well. So what you can look at as well is the avalanche shape, for example. And there's a prediction for, so the avalanche shape is if you look at the stress drop and you look at the stress drop velocity, this will give you a certain shape. It goes from 0 to 0, basically. And the mean field prediction is that this is just a parabola, whereas we see in the simulations that it's asymmetric, so there's it's not the mean field one. But as soon as you increase the shear rate or you increase the system size over which you measure, you see that it becomes symmetric. So it's in the same spirit. Instead of seeing something individual and an individual avalanche, you see a superposition of many avalanches which make the thing more mean field-like. So I agree. So now, if you want to describe mean field descriptions, a very important question is whether these athermal dynamics are effectively thermal. I showed you in the picture of the simulations, you had this Eshelby around, but due to the long-range interactions, there's some noise created elsewhere. And there's this idea in the community that, and this is a very tempting idea actually, that this mechanically created noise, there's only this noise because there's no temperature, can be encompassed as a thermal noise. For example, in the SGR, soft glass rheology theory, the idea is that you have a potential energy landscape, and when you have a mesoscopic region, so the stress fluctuations will help you to overcome a barrier, and so the escape rate for this event should be Arrhenius-like. So, but we believe that this is flawed because when you have an Eshelby somewhere, this will induce displacements everywhere, but these are persistent. It's not like a random kick that relaxes again. So, and in the mesoscopic model, if we measure, for example, the yield time versus the yield energy, we clearly see that this is more like a power law dependency. So we believe that the analogy with the thermal fluctuations is false. Sorry?
Yield time is
when you overcome the barrier. So you just, in the mesoscopic simulations, it's easy because you just see individual events. Yeah. Yes, if there is a real temperature, then maybe there is. So there's Anna Lemaitre who was studying these things, and I believe STZ might work in thermal systems, so that you have both things, and I don't know how they combine. This is one of the future things that we want to look at, but at truly athermal systems and the athermal limit, we see that this is not a good description. And so our understanding of the athermal dynamics is the following. So it's very dramatic, but here again you see the potential energy landscape picture. So if you assume that for a local mesoscopic region you have this configuration and you have a finite shear rate which will lead to a stress, then the stress actually will act as a tilt of the potential. So this is described here. So the dynamics for the strain will be in the overdamped limit will be just this. You have the change of strain, which is given by this potential.
Why is strain control like this? I don't understand.
Yes.
You are doing strain control, not stress control.
I do strain rate control.
So strain control doesn't change the enthalpy. You have to do stress control in order to change the enthalpy. That would make E going to E minus sigma external gamma V or something like this. That really makes it.
This is when you impose a stress. So
yeah,
this picture is for imposing a stress.
But for imposing stress,
Yes.
you do it strain.
Yes,
So I'm confused.
Okay, maybe we can discuss this later. Maybe you see there's a difference in.
Of course, there's absolutely.
Let me specify.
Yeah.
This is a local landscape.
Yeah, it's a mesoscopic.
Yeah, but sigma is a state variable that the system responds to. It's not something external that we put into an effective energy. Anyway,
So let's say there's an Eshelby happening
I
somewhere.
disagree. Go on.
So let's say there's an Eshelby happening somewhere. An Eshelby, and then elsewhere there are this displacement, introducing a stress. How would you? I would describe it like this. Okay, let's discuss this later. And then, since we, as you say, we impose a shear rate, so this stress will have some dynamics, so this part, which is given by the elastic response and some noise. I don't say how this noise looks like now. And the yielding point will be when the energy barrier has disappeared. So then the configuration can change. And so this is not like overcoming a barrier with some effective thermal fluctuations, but it's like a diffusion of the area, barrier height with this plastic noise, mechanical noise, which is a different process, and it's yielding actually this power law behavior. So there are many, there was already said there are maybe too many theories that are already there. And we didn't introduce a new one, but we looked into one that has been introduced more or less at the same time as the SGR theory and the SDZ theory, partly even by the same authors of the SGR theory. And so what we believe is a good description is the mean field description, let's say, is the Ebro-Lequeux model. So there you describe the evolution equation for the probability distribution of mesoscopic stresses in the following way. So you have the time evolution of the distribution, which is given by the elastic linear response here. Then you have here a yielding term. Once you're, this is a Heaviside function. When you're above a critical stress value, you will yield with a rate 1 over tau. And then there is the corresponding gain term due to the yielding, which is a resetting of the stress to 0. And then, most importantly, their assumption is that the fluctuations that are created elsewhere in the system due to the Eshelbys all around is diffusive. And again, this is different than the SGR description because you don't have the potential or the retractive force that would come from the potential. So this is a different description. And this is quite boring equation so far. It's just linear. But what they have as an additional assumption in their model is that this diffusion of the stresses should be related to the plastic activity around. So you have the diffusion coefficient, so the strength of the white noise here, is proportional to gamma of t, which is the activity, so the number of Eshelbys produced per unit time. And with this, the model becomes highly non-trivial because it becomes nonlinear. And you see that there's a regime when alpha is smaller than critical alpha, so this coupling constant here between diffusion and activity is smaller than a critical value. You see that you obtain the Herschel-Barkley behavior here with the yield stress and then with the shear rate dependence with an exponent exactly 1/2. And again, the nice thing about this model is that it has very, very few ingredients. And only after adimensionalizing this equation, the only parameter that's left is this alpha and the shear rate, of course, that you impose. So
How do you get it analytically?
it's analytically, yeah. It's an analytical result. And you need to go to nonlinear order to obtain this. So it's not coming from the linear response. And so you see that since there's only one parameter, this alpha, both the yield stress as well as the amplitude should depend on this alpha, meaning that there's a parametric relation between the adimensionalized yield stress and the adimensionalized amplitude, which is just a quite strong statement. So let us now test all of the assumptions and the predictions of the Hébreux-Lequeux model. So first prediction was, I was saying, it predicts this 1/2 exponent in the Herschel-Barclay law. Well, as I showed you, very close to the shear rate going to zero limit, it's not true. I had very different exponents here. But if you're fitting flow curves for a larger range of shear rates and small systems, you see that, well, these are not too badly fitted by, even very good actually here in the Lennard-Jones simulations, by a law which is given by this. And so maybe if we concentrate into this regime instead of the critical regime, very low shear rate regime, we can recover the Hébreux-Lequeux description. So let us test the underlying assumptions. One of the important assumptions was that the yield stress is, so just show the equation again. One of the assumptions is here that the yield stress is the same everywhere. That was what you were saying. And another important assumption is here that the yield stress is going to zero after yield, which is also maybe not so true. And the third assumption, and this is the most important one, is that the noise created by the HOB around is diffusive. So the first assumption, of course, is wrong, because the yield stress is in reality widely distributed. That was what you were saying. So, and we measured this in the molecular dynamics simulations with Francesco and Julien Olivier. And so you can redo the calculations for Hébreux-Lequeux. And actually you find that even if you put a distribution of yield stresses, you get, again, this Herschel-Barclay law, and the exponent is robust. So it's robust, and the yield stress and the prefactor are distribution dependent, and as long as you assume a reasonable distribution, because here there are some fourth moments of the distributions appearing, so you need those to be finite. So, but this isn't normally the case. Okay. Then the next assumption was the stress diffusion. And astonishingly, if we looked at, so this is now the mean stress differences in time for different densities, we see that this is really, really nicely linear. So this, of course, this is the short time regime. Since we are yielding, at some point we must level off. But here, this first small time regime is very much linear in t, which indicates that the stress is really diffusing with a normal diffusion. And so we did the simulations for different densities, and now you see the strongest Herschel-Barclay prediction, which is that this yield stress should be a parametric curve of the amplitude. So I plot here the amplitude as a function of the yield stress in adimensional units, and we see that for all the densities that we probe, and which give very different A and sigma yields if you don't adimensionalize, they all fall within a certain range here, and the error bars are more or less within the Herschel-Barclay prediction. And what this is indicating is, first of all, maybe Hébreux-Lequeux prediction, sorry, and the Hébreux-Lequeux prediction seems not to be too bad. And the second result is that this alpha value, since this is a function alpha, you can deduce alpha here, is density independent. So the coupling between diffusion and plastic activity does not depend on density. However, there's an inconsistency with the Hébreux-Lequeux predictions. Once you calculate this alpha from the flow curve, and you calculate the alpha by measuring the diffusion coefficient and the plastic activity, you see that there are orders of magnitude different. And this, we think, is due to the third assumptions, which is in the Hébreux-Lequeux model, which is the oversimplification that the stress is set to zero after yield. So you can correct this form, and typically, since the stress is going to about 0.2 times the yield stress, if you correct this, so there will be a delta sigma squared appearing here. This exactly gives you this 25. 5 to the 5 squared gives you the 25. So it seems quite coherent. And so our proposal is maybe there's a quite universal behavior further away from the critical point. And you have generic behavior. You can describe the flow curve through a coupling constant, which is only depending on the form of the stress propagator and not on density or other ingredients. So I come to the conclusions. So I presented you some results about the athermal sheared, steadily sheared systems. And so my first conclusion is that I believe that athermal sheared disordered systems are athermally sheared disordered systems, meaning that we should not consider that athermal systems can be described effectively by a thermal description. So this would be in contradiction to assumption of the soft glassy rheology, but also of the shear transformation zone theory. And then the next thing that I showed you is that further away from the critical point, it seems that mean field approaches do not work too bad. And that you can define a coupling constant, which gives you the strength of coupling between the stress diffusion and the rate of plastic activity. And this parameter characterizes for you the flow curve. And it's density independent. And we really would like to test this concept in other model systems and maybe see whether we can do this even in experiments. Okay, so I thank you for your attention, and just this is acknowledgement of the money given.